Hi everyone, thank you for watching this tutorial. In this tutorial, I've introduced how to set up a custom data servers and realize your own checks on the Nucleome browser. We have prepared a tutorial using published single-cell high-C data. And you can clone this GitHub repo. I will provide the link of this repo in the description box of this video. So here we actually you can follow this tutorial by downloading the raw data from the geodatabase, pre-process the high-C and chip-seq data into the big bat file format or the .hic format, and then start data servers. We also provide a demo dataset, as you can see here, that you can directly use this demo dataset and set up local data servers and realize them on the Nucleome browser. In this tutorial, I will not go through the pre-processing step. Instead, I will just use the demo dataset. And we have listed different requirements for different platforms of the computer, like Linux and Mac OS. And for this tutorial, I will show you how to set up local data servers on a Linux machine. And to do that, most of the tools that we will use in this tutorial has already installed. Those tools are like the Juicy tools and the fetch size and batu. Big Bad are used to pre-process the dataset, which we are not use. The only tool that we will need to install is this one called the Nucleome Server. We can click this link to download the right version of the Nucleome Server. First, we need to decide the type of the machine we are using. So here I have prepared you a command that we can copy and we can copy and paste into the terminal. So here it says AMD 64. So here, if we click this link, it will lead you to the latest version of the release of the Nucleome Server. And here we can click the release here. And then we should download the right one. So this is the one we need to download. Okay. We use wget to download this version of Nucleome Server, and then we use star to decompress it, and then we can see that we have already decompressed it. And we also need to be able to run this too, so we can use this command. As if we can successfully run it. And as you can see here, it shows help description of those tools, meaning that we can already run it. And then we can click the step 6 or section 6 here. So here is a session the tutorial we will use. So here we can just copy this and clone this repo into our local machine. Then go to, so here we can see that we have already cloned the repo and including the demo dataset into our local Linux machine. And then to do that, it says that we need to actually open a configuration file, which is an Excel file, and you put the correct root put the correct path of the root directory into the B2 cells. So here we can use the pwd command to do that. So we type pwd And this is current complete path of the folder or the repo we just cloned from the GitHub. And then we can so we can go to this folder here and demo data, and so open this configuration file. Okay. I will briefly introduce what it means for the configuration file. So basically, there are multiple datasheets in this Excel file, and the first one is called config sheet, which include a very important variable called root, indicating the complete path of the root folders. And so for this example, we should put this we put this value here. Delete it and paste it. Yeah. Importantly, don't forget to save this file so that Nucleome Server can read the correct variable numbers. And in the second sheet, it's called index, indicating how many data sheet we have for each data set. For each data sheet, I usually put like the data set from the same type of experiment as one data sheet. So for example, here I have two data sheets, one called Hi-C and another called ChIP-seq. So Hi-C basically hosts all the single cell Hi-C and population Hi-C content max, and for the ChIP-seq datasheet, it will host all the ChIP-seq peak files. And the first column indicates the genome assembly version. Here we use MM10, and okay, let me zoom in a little bit. And in the second column is the name of the datasheet. So here we have the Hi-C, so we named the datasheet as Hi-C, same as here. And the third column is called tab, which is used for future development, but you can just put a track here. And the fourth and fifth column are very important. So this indicates column IDs for different variables. So the name column indicating the column IDs of the short label of the track, and the values are other information of the track, which I will talk into details. So for example, let's put a Hi-C datasheet as example. So here the column A should be the short labels of each track. So here we have the population Hi-C and 8 single cell Hi-C content maps. And the BCD, the B, so the first variable is the URI of the data, which indicates the relative path of the data to the complete root complete path of the root directory. So for example, here this is our root directory, and our data is stored under the demo folder. And so for Hi-C, there's a subfolder called Hi-C. And so these are all the single cell Hi-C and population Hi-C. So we put the URI like this. Remember, this is relative path to the root directory. And the second variable is called meta links. So if your dataset can be associated with URL, you can put that URL here. So when people click the track names, it will open that URL in the web browser. And the last variable is called long labels. So here I just use the same labels I just use the same as short labels here. So as like this. And another ChIP-seq dataset is also very similar. So the first column is short label and the URI, meta link, and the long labels. Now you can put different attributes in different columns, but just make sure that the columns IDs here correctly match well with the real orders of the columns. And after we have saved and also put the right root values in the config sheet, we just manage save it and we can close it. And then based on this tutorial, we already make this step so we can run the Nucleome server and test it without an issue. And then we can run this script to start a local data service. So I can copy and paste it here. Yeah. So here, let me see where I put my Nucleome server. So I think I put Nucleome in another place, so I can copy it into the scripts folder. Okay. So now we should be able to run this command. Okay. So if you see this type of information like a loading sheet, and this is name of the data sheet and different tracks, it means that you have already successfully create the local data servers, and by default, it will create that using the port 8611. And we need to, then we can also create another local data service to host the 3D files, 3D genome structure files. To do that is also very simple. So here are all the 3D genome structure files is also located, stored in the demo data folder, and there's a subcode called 3D. And see here, we have provided 20 3D structure models, 10 for each cell, as you can see here. And then we can copy this command and run it. Okay, now we have started both the genomic data servers and data servers for 3D genome structures. Next, we should open a web browser. We recommend you to use Google Chrome browser or Safari browser, and Google Chrome will give you the best visualization experience. You can click this link. And if you use the default port for the genomic data servers, you should already load that. So here is the home page of the Nucleome server, and if we click start, and there are some public sessions that you can try. Here we just click the start a new genome browser. Okay, so by default, this is what is the default view of the Nucleome browser. It actually realize a large regions in chromosome 1 and chromosome 2. And we can click this configuration button on the top right of the panel. Click it and select the right genome. So here we actually load data in mouse MM10 genome. Okay. As I said, if you are using the default port, the local data service should automatically load it. So here we can see that at the end of the different. So here each in the drop-down menus, you can select a different data sheet. So all the others are the public data tracks from the 40 DCIC, but the last two are the two local data servers we just started. So we can click high C and to load population high C and maybe two single cell high C, and click submit. So you may see this loading forever. This is called for this demo data. We only provide data in the smallest chromosome, which is chromosome 19. So we can type chromosome 19 and hit enter key. Okay, so now we can see the data. We can resize the windows to make it larger. Okay, so the first check is population high C, and the two others are single cell high C. We can open another genome browser panels and load and load all the ChIP-seq checks. So by default, the big bad files is in the full mode. We can just make them into the compact view. All of those will show like this. And so for the and then we can also initiate a 3D structure panel like this. We can arrange it in different positions. So on the left, we show different genomic tracks, and on the right, we will show the 3D structures. And remember that, so here, our 3D structures is rendered in this part. So we can just see if we can. Oh, no, not this one. Okay. And okay. So now we can see that this file server will have host our 3D structures into this URL. And there are 20 different models for 2 cells. And we can just copy the link here and put it into the structure URL box. There we should use a get, so get. See here, so right link is get model. And then, so here, this is model 1 for cell 1. And we can duplicate this and load a model for cell 2 so that we can compare different models in different cells, single cells. So for example, we can visualize the first models for cell 2. We can click enter. As you can see that this models looks a little bit different because of course this is a model for different cells. You can change the sync view ID so to assign the different 3D structures for different ID so that you can rotate or zoom in for each 3D structures. And we can also set different styles to visualize these 3D structures. Importantly, in the Nucleome Browser, you can effectively navigate across different panels or even web portals. So for example, we can click this button and change how we want to highlight on the 3D structures. If we choose the rightmost button, which means that only the structures that are highlighted on the other panels will be shown on the 3D structure panels. So for example, we can highlight this region. So we can see that those regions highlighted are shown here. And zoom out. Try again. So as we move the highlighted regions on the left, the corresponding regions will also be highlighted on the 3D structures. This is very useful if we wanted to compare different cells or different conditions. So for example, here we highlighted pairwise regions that show differences in between the first cell and the second cell. And we can also see the differences on the 3D structures. So it looks like in the first cell, those two regions, they have a single cell high series, means that they may probably close in in 3D space, and indeed it looks like in the first cell, these two regions are closer in the 3D structures as compared to the second cells. And importantly, you can also superimpose the big wig tracks onto the 3D structures. Let me show you quickly. So here we can load some public 40N big wig tracks. So for example, let's load the DOM ID. Okay. And then we can click this button. So by default, the colors of the chromosome is based on the chromosome ID. And if we click this button, a box will show here, showing that you can drop a big wig track here, so that the colors of the chromosome will be based on the values of the big wig tracks. We can click this button to view the descriptions of these tracks, and if we click read more, it will lead you to the web page on the 40N data portal. So here we can click this button and drag it to the box here. So here the colors just indicate the DOM ID values of the tracks. And we can also show different regions. So for example, we can show them the whole genome, and it looks quite nice. We can also show the one chromosome or the current viewed regions or the highlighted regions. So I highlighted a small region, and it only shows a small part on the 3D structure. And last but not the least, we also provide a powerful interactive scatter plot analysis tool. You can click this button. So basically, it allows you to select tracks for X and Y axis. Okay. So here, each dot is one genome bean. And if you highlight it on the genome browser on the left, those highlighted regions will be shown on the scatter plot. And if you click this button, use this lasso selection tool to select some points on the scatter plot, those regions will also be highlighted on the genomic tracks. Okay, I think that's pretty much okay. So if by default, if you use the default port number, the Nucleome Browser should automatically load the local servers. If you use other port numbers, or if the service not show up, you can manually add the data servers to the Nucleome Browser. To do that, I will show you quickly. So you can click this button and click the setting buttons to add different data servers. So for example, although we already see this custom data service, we can also manually add it. So name and this. So you can replace the port number if you use other port numbers here, and click the refresh button. You should see the status as active. And you see two data checks. We can also add the 40N public data servers like this by typing /d and hit the refresh button. Okay, so we can now see all the public 40N data sheet, like here. And click this button, we will go back to the Genome Browser views. So basically, I think that's it pretty much the tutorial that it's very easy to use. I think after you clone this rebel to your local machine, all you need to do is first you should install the correct version of the Nucleome server, and then don't forget to change the configuration files. And we have tested this in different machines. You can follow these tools also, starting from the raw data and processing the chipset data and the population HiC, single cell HiC. So you can view all the data in all of the chromosomes. Okay, thank you for watching.